Welcome to Tic-Tac-Toe the Hard Way, the podcast in which a writer and a software engineer train an AI to play a simple game.
And take a hands-on approach to exploring the very human choices that go into training a machine learning system.
Hello, David.
Hi, Yannick.
Looks like we're back.
It seems so.
And on to the second half of this, the somewhat more exciting bit in some ways.
This is where the stakes are doubled and anybody can win, although there's no chance I will.
We'll see about that.
Yeah, fine.
So to remind folks, we're at a point where we can now start looking at Tic-Tac-Two, which was the true objective of what we wanted to learn how to play. And that's a game you invented, David. And could you just remind listeners, what are the rules of Tic-Tac-Two?
They're the same as tic-tac-toe with a couple of exceptions. You win the same way, and it's an X and a 0 and people play. The exception is that in order to win, a player has to put 2 marks into a square. So normal tic-tac-toe, you slap in your X, you own the square. Tic-tac-two, you've got to get 2 X's or 2 O's into a square. Second rule is that once a game, each player is entitled to play 2 of their marks in a single move. So
anywhere on the board, right?
Anywhere on the board, including both in the same square, so you own that box instantly. This is, we think, complex enough that it might make sense to actually use machine learning to do this, to play this game. Whereas traditional tic-tac-toe, if you really wanted to train a system, you would just program in the rules. This one is actually a little bit more complex than that.
It's a thing that feels like, there's a little bit more strategy there. When to play that double, when to take advantage of that kind of thing. That might be worth learning. It's probably one of the things that could be programmed if we tried hard enough. But thankfully, we don't have to. We have machine learning.
Yes, and it's so much simpler than programming the old way. I'm sorry. You're talking to somebody who has spent weeks just trying to generate randomly played games to serve as data to put into the tic-tac-toe system so it can learn from it. And it was just at an uninteresting level of JavaScript programming or node programming. It was just a total pain in the butt for some of us, who are less than professional developers.
That is where a lot of the work goes and where it's different from regular programming. In some ways, it's interesting because that focuses on the data, not on sort of a ton of new logic or strategy for the game itself. And that's the part which in some ways you could say is like, in some ways easier than regular programming because you don't have to think about what's a good strategy for it. You just have to think about like, how do I generate some data for this? And then we see what the machine can learn from that.
Yes, the data generation part was difficult for me for, as I say, uninteresting reasons. Once the data is there, then the training is relatively straightforward.
That's a great segue into sort of talking about what we've done since Tic-Tac-Toe wrapped up to sort of get towards Tic-Tac-Two. And for me, it's somewhat similar to what you described. So while you're generating data, for me, it's about changing the environment in my reinforcement learning agent. And the primary work I had to do is adapt the environment to play with the rules of Tic-Tac-Two and give the agent feedback when it makes moves. So I have to write new logic for validating what's a legal move, because now you can play more than one of your marks in a cell, or you can play a double, but there are some other things that aren't legal. You can't play 3 or 4 marks in a cell or that kind of thing. So a lot of the logic was really in just what are the mechanics of this game? Like what are the legal things? What are the illegal things? That was a bunch of work. The random opponent that my reinforcement learning agent trains against got a little bit of extra code so that it randomly plays a double somewhere during a game. But other than that, it was actually pretty similar to the tic-tac-toe agent because the board size is essentially the same. The game just continues playing even though the cells have a mark in them already.
Does your agent, when it's randomly playing a double, does it play a double in every game? And does it have a preference built in about where it will play it, towards the beginning, towards the middle, towards the end, or something like that?
I don't know if it plays it in every game. It's pretty likely. I think I coded it up as like every turn, if it hasn't already played a double, and a double can be played, there's like a small percentage that it will play a double. And I think that was somewhere between 10 and 20%. I can't remember exactly. Probably around 20%. So it's pretty likely that it played a double at some point in time. But I didn't insist that it did or try and do any more fine tuning into whether it should try and play that early or late. I just was like, 20% probability to play a double if you can.
Mine also, when I'm generating games, same thing. Each turn, if the player hasn't played a double, then it rolls the dice, so to speak. And for whatever reason, mine is rolling an 8-sided die, so 1 out of 8 that it's going to play a double during that turn.
Okay.
I don't
Yeah.
know.
You just picked it. Exactly. We don't know the strategy for this game. That's the good thing. We don't really have to think about like, oh, what's a really good way to play tic-tac-toe. So it's just kind of random. I'd say one other part of the code that needed to change, and everything I've described is essentially just sort of writing JavaScript code in terms of sort of TensorFlow related changes. That was a bit in the data representation that the agent gets. So the board representation is obviously different because there's just a lot more cells, but that just sort of grows bigger. It's not qualitatively different.
It's still a 3 by 3 grid.
Yeah,
The board is, but each square can hold up to 3 marks, XOX or something.
exactly. So it just sort of expands in length, but doesn't really change that much in sort of interestingness. There's sort of one extra bit of data that the agent gets, which is whether it has already played a double in the game. So it keeps track of whether it's already made a double, and that's part of what gets sent to the agent when it's trying to decide whether to make a move.
Makes sense.
And yeah, that was the main change to the input space. The other thing that changes is the action space. So the moves that an agent can make do change. So in tic-tac-toe, you can basically make a mark in one of 9 cells. It's just a thing on the grid. In tic-tac-toe, there's a lot more options. So you can make one mark in any of the cells. That's free. Or you might be able to make 2 marks, but those can also be distributed in any of the cells. So you can imagine, you have your first 9, and if you're playing a double and you put your first mark in the top right corner, you can put your second mark in any one of the other 8 positions. And if you repeat this for all of the positions, you essentially get to a space of about 90 different actions that the agent can take. So that was another sort of difference in how the model code looks between tic-tac-toe and tic-tac-toe.
So it is a little surprising that it doesn't go from 9 possibilities to 27 possibilities, because 3 possibilities in each box times 9. I can do that math. That's 27. But because of the possibility of a double, the number goes way, way up, the number of possibilities.
Yeah, because you have this combination of multiple things that each have a position that makes a difference.
Okay, so it's a bigger possibility space,
hmm
which sounds good and sounds more complex.
Indeed, yeah. So I think, yeah, the complexity went up a bit. But one nice thing is like essentially the rest of the code stayed the same. So it's really just the environment. But in terms of like the algorithm bit, which I talked a bit about before, I didn't have to change any of that.
So those are all changes that you had to make to your code for training, but you also had to make some changes to the thing that you think of as a viewer and I think of as the player,
Yeah, definitely did have to make a new viewer so we could watch these games unfold.
and have an random agent play the games as well.
Yeah, that part didn't change too much from the previous one. That was also there in the previous viewer. Here, it was really the logic for like rendering the board and the legal and illegal moves.
And it's beautiful. So
Oh, thank you. That was kind of the changes on my end. How about you? You talked about sort of needing to generate training data and that taking a while. What does that look like?
uh, ultimately, I think it's getting there. Maybe it is there. But so again, this is a random game generator. So each move looks at a board and finds a legal move to play randomly and plays that move and then does the whole thing again. And at each move, it checks to see if somebody has won. And if the game is over, somebody has won, or there's a tie actually, then it saves the game. It saves the game once again only if there is a winner, because we only want moves, that is boards plus the next move that's played on that board, that are taken by the person who won a game, because they're trying to teach the system how to win a game, not simply to play it without caring about winning. So the part of it was relatively easy, which is the board representation, as you talked about. When we were playing standard tic-tac-toe, the board is represented internally in the code in my random game generator as a string of 9 characters. The characters are either an X, an O, or a dash indicating unowned. So that's straightforward. And it's also, I think, straightforward for doing it for tic-tac-toe, except there are 27 possibilities. Each square has 3. So that part, I think, is relatively straightforward.
Mhm.
Okay, good, because that's what I did. And then you have the issue of we also need to know who the player is for each move, because again, we only want moves
Mm.
from the winning player. So that has to be in there, maybe.
I guess you want the moves for the current player. You want to know who made the move. Was this a move by X or by O?
Yes, because I'm generating a JSON file that records all the moves in any game that has a winner, including the moves by the person who lost. And that's so I can check to make sure that the game was legitimate and things like that. Although we're only going to train it on the moves that were made by the person who won the game. And so, yeah, it records who the player was. And it records also, does the player have a double to play?
Mm.
Did the player already use up their double? So that's encoded also, but you had to help me with that because that's totally new information compared to tic-tac-toe. And then also, of course, the label or the move itself I have to record. And that's different than in tic-tac-toe because there's always a possibility of a single turn having 2 moves, right? X plays a double, makes 2
Yeah.
moves. And I went around and around for a while wondering whether I should represent a double as 2 moves, which would be straightforward, right? It's the same thing. And it's just, you got a board, you play a move, and if it's a double, you let that player play again, a move and a double, a move, a board and a move. Or it's a single turn that has 2 moves
positions.
And I was taking that first route, turned it into 2 moves because it seemed simpler. But you had me do it the other way.
Yeah. I think the problem we ran into, I remember us discussing this, but I think the sort of problem we ran into conceptually is if you want to encode that turn as 2 moves, when you get a prediction from the model, how do you know whether you should do another one? Which is basically, how do you know you want to play a double this turn if you sort of encode it as 2 separate things that you're going to get from the model? So that was a bit of a conceptual gap in how we would use it to play the game.
Yeah, I can see that. Because if we did it my first way, which was coded as 2 turns, presumably it might learn that once a game, the same player may take 2 moves, which is what we wanted to learn, right? We wanted to have this idea of a double. I would think, based on my deep intuition into machine learning, that it would learn that. It's okay sometimes to take 2 moves for the same player.
I guess maybe one different way to think of it is then you need to figure out how you represent the difference between 2 simultaneous moves made by the same player and just sort of 2 moves. Like the agent pretty much only has access to the moves it's making in the board state. So I couldn't really see a way where you could sometimes ask the model, give me 2 moves in a row, and know that that's different from give me 2 moves and somebody else has played in the middle. Like there isn't really a good way to pose that question to the model in the first scheme, or at least none that we came up with while discussing this.
Even if it had learned that once a game, sometimes a player will play 2 moves in a row, getting the results back would be really complicated.
But if we can't express this as a problem, there's no way for it to learn that. So I'm describing it as like what we do when we're trying to play the game. But in the training part, it's the same sort of issue. What's the difference between, like, you just give it a bunch of moves that the winning player made. Where does sort of the concept of 2 moves in a row come from? That's what was missing. Because essentially, the only moves it sees are all of the moves it makes. So it kind of sees all of the moves in a row.
Does this go back to the question that we talked about before about whether for training the system, one needs to give the system an idea of a game, which consists of some set of moves, or whether you're just training it on moves, that is boards with the next square predicted?
It does relate to that. And definitely because you're just training it on moves, there is no relationship between them. So if there were a larger concept of a game, there might be some way to encode it in that way, but you'd still have a bit of an issue, I think. But yeah, it's definitely at least partly constrained by the fact that like it's just looking at a board and making a move.
So you had me represent moves, including double moves, in a particular way that I totally trust is right, but I don't fully understand why it's that way. Can you re-explain that to me for like the eighth time?
Yeah. So one change we had you make was in the tic-tac-toe problem. The way you expressed which cell to put a mark in was you take an array of length 9 and everything would be 0 except the one place where you want to put that mark. And you'd put a 1 in that spot.
So if it was, you're supposed to play square 2, it would be the second 0 becomes a 1.
Yes. So that's what we did in the tic-tac-toe situation. But now, and in this one, many of your moves are like that because you're only playing one mark. So most moves that an agent make will have that similar representation. But sometimes you want to say, I want to put 2 marks down. And the way we do that is we just put a 1 in that other place that you want to make a mark. So now you have 2 1s inside your array and the rest are 0s.
Huh. I think I just found a bug in this because suppose I want to play 2 marks in 1 square. Huh.
That is a good point. This representation probably wouldn't work super well for playing 2 marks in 1 square. Huh, that is interesting.
Next time we do this series, we'll address that. Because it probably is an important move. You play 2 marks in 1 square, you
Yeah,
own the
to
square,
own a
right?
square
Yeah.
immediately would probably be pretty handy. So yeah, that's an interesting limitation to discover now as we think about it. Yeah, good catch.
Okay. Woo! Let's just end it here. I mean, this is a victory for me.
Yeah, you're getting it. You're getting it. You've now actually have a good conceptual understanding of what that representation is. So I say victory.
Yes. Meanwhile, I'm crowing about competitive victories as if this is.
I'm just happy about the learning.
That's the difference between you and me. It's one of many ways in which you are a far better person than I am. And I don't actually mean this competitively. It's my little joke. Anyway.
But it's a good point. Yeah, the representation we chose actually misses encoding the double in one place well. So that's a good observation. It does sort of maybe give a bit of a handicap to the data that you've generated.
So that presumably that set of information is enough to train a model on. It's the state of the board. It's does the player have a double left? And it's a move, a prediction, or a label that can have 1 or 2 squares indicated in it as moves.
That's enough. There is a little bit of a change that this is going to imply for your training code. And you're going to need to change the loss function used. And we talked a little bit about loss functions in a previous episode. So I'll just say real quick, the loss function is a function that computes sort of how correct a prediction is. Given some ground truth data and a prediction, that loss function is going to be a signal to the training algorithm of how correct that prediction was. And now we just need a loss function that can handle evaluating the multiple positions, the fact that sometimes there's more than one in the array. So there's some other math function that we use for that. So that's like one line of code that's going to need to change from your tic-tac-toe game to this one.
It has a super cool name, doesn't it? The loss function that you want me to use?
I don't know if it's super, super cool,
Oh,
but I think
is.
we've tried to stay away from the mathy terms in the jargon. So we'll keep that just between us.
No, I want to feel super smart.
So you say, tell the people what loss function.
Well, it has the word entropy in it, and that's enough for me.
Okay.
Well, it's not enough. What is it?
You tell them.
I'd have to look up my code. Entropy. Cross current entropy.
Yeah, but I thought we discussed not to go down
Schrodinger's.
this route.
I'm not going down. I just want the word. I want to feel cool for 1 minute. Is that too much to ask? Fine. Fine, Mr. Math Guy. I have a question about the term loss function. I'm just curious. Do you know why it's called a loss function? What's being lost here?
It's sort of another term for error, like the difference between what you expect and what you get. You could think of as a loss. So
Okay.
you lost some accuracy, maybe. I actually haven't read a history of that, but that's sort of what I picture when I think of that term and what the math is doing. That's what I think of. So I think that's our data. We have our data generated. That's kind of what we need, as usual, to do training. I've updated my agent.
So I'm generating data. You've got your reinforcement learning system adjusted so that it can handle this new rules. we are ready to go on to training, we think, right?
Yeah, I think in the
At
next
least I
episode
am.
we'll talk about training this. Yeah,
Okay.
and we can see how they do. Yeah,
As usual, I am confident I will crush you.
confidence is important in learning.
And for being a jerk. So,
It makes the learning stick. I look
Okay.
forward to that.
Okay. Well, see you next time.
You've been listening to Tic-Tac-Toe the Hard Way with your hosts Yannick Asogba and David Weinberger. This is a production of Google Pair, with thanks to Rebecca Salois, Eric Johansson, mixer and editor Brian Gordon,
And the entire Pair team of developers, researchers, designers, artists, philosophers, and more. A special thanks to Nikhil Thorat, who created the music with help from AI by Google Magenta.
You can find links to code and more in the show notes and at our website, pair.withgoogle.com/thehardway. Once again, that's pair.withgoogle.com/thehardway.